The global AI boom is facing a silent, invisible wall. It is not a lack of data, and it is not a lack of clever algorithms. It is heat. As we push the limits of silicon with massive AI-specific ASICs and high-density GPU clusters, we are reaching the physical limits of traditional cooling. The roar of massive fans and the specialized air conditioning of data centers are no longer enough. We are entering the era of microfluidic cooling, the technology that is literally going to keep the brain of the next generation of artificial intelligence from melting. The mainstream narrative is that we just need more power and more data centers to achieve AGI. But the contrarian reality is that power is not the bottleneck. Density is. We are packing so many transistors into such small spaces that traditional air cooling, which relies on moving massive amounts of chilled air over metal heat sinks, is becoming fundamentally inefficient. In fact, in many modern data centers, nearly 40% of the total electricity consumed goes solely to cooling the hardware, not running the actual computations. This is an environmental and economic disaster waiting to happen. Microfluidic cooling represents a paradigm shift. Instead of bringing the cooling to the chip, we are building the cooling inside the chip. Imagine a network of microscopic channels, thinner than a human hair, etched directly into the silicon or the substrate of the processor. A specialized coolant fluid is pumped through these channels, absorbing heat directly from the source of the heat-generating transistors. This allows for a heat transfer efficiency that is orders of magnitude higher than air, or even traditional liquid cooling. But here is the non-trivial challenge that the industry is currently grappling with. It's called reliability at scale. It is one thing to demonstrate microfluidic cooling in a laboratory setting on a single prototype chip. It is a completely different challenge to maintain these systems across a data center with tens of thousands of processors. We are talking about high-pressure fluid systems operating in direct contact with sensitive electronics, 24 hours a day for years on end. A single leak or a microscopic clog in one of those channels could lead to the instant destruction of a multi-million-dollar hardware cluster. This technology is already moving from research labs to the real world. Major players like Intel, TSMC, and specialized startups are reporting breakthroughs in integrating microfluidics with advanced 3D chip stacking. By cooling individual layers of a stacked processor from the inside, we can achieve performance densities that were previously thought to be physically impossible. This isn't just about making AI faster, it's about making it sustainable. Microfluidic systems can operate at higher temperatures than air cooling, which means the waste heat they generate can be more easily reused for heating buildings or industrial processes, turning a data center from a heat sink into a heat source. The geopolitical stakes of this efficiency race are enormous. Countries that master high-efficiency, high-density AI infrastructure will have a decisive advantage in the race toward AGI. We are seeing a massive trend toward sovereign AI infrastructure, where nations are repatriating their compute resources and building next-generation data centers using advanced cooling technologies to reduce their reliance on the global power grid and the traditional GPU supply chain. As we look toward the future, the boundary between mechanical engineering and semiconductor design will continue to blur. The computer of the future won't just be an electronic device. It will be a complex fluidic system. This is the ultimate goal of AI infrastructure: to create a digital brain that can think with incredible speed while remaining as cool and efficient as the biological brain it was designed to emulate. The future belongs to those who understand that the most important breakthroughs in AI might not happen in the code, but in the plumbing. We must prepare for a future where computing is as much about managing fluid dynamics as it is about managing bits and bytes. The era of the noisy, air-cooled data center is ending. The era of the silent, fluid-cooled AI brain is here. It's time to stop thinking about AI as just software and start understanding the incredible physical infrastructure that makes it all possible. Stay informed, stay critical, and keep your eye on the flow.